live. Okay, so we are going to do the end of chapter problems for chapter 6. So let's bring that back up, and let's bring up the textbook. We are going to do 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62, 64, 66, 68, 70, 72, 74, 76, 78, 80, 80. Okay, so we're going to do 32 straight through 80 before we take a break. So 32 through 80. Excellent. That'll make it easy after a fashion. Okay. 32. Cytosine, a constituent of deoxyribonucleic acid, DNA, can be represented by the following molecular model. If 0.0010 moles of cytosine is submitted to combustion analysis, how many moles of CO2 and how many moles of H2O would be formed? Ooh, that's a good question. Okay, so that means we're going to need to figure out the the chemical formula of cytosine first off the bat. So we have C4H 1, 2, 3, 4, 5 N3O. So that is what we're going to be burning, and we're subjecting it to... Okay, that's inconvenient. What sort of product would we make from the nitrogen, I wonder? Because when you burn it, it's going to make O2. All right. I wonder if they tell us that specifically, or if they tell us what we should expect. Oops, that's not what I meant to do. All right. Because nitrogen and oxygen can produce a huge number of things. That's why I avoided nitrogen-containing compounds in my description. And I noticed that none of these examples include nitrogen. That's why I always just either gave you the mass percent of nitrogen, or... Okay, this is an annoying problem just for that reason alone. All right, so... Okay, so the nitrogen isn't going to be involved in the CO2 or the H2O. So let's just go ahead. We're going to have 8 CO2 and 5 H2O. Yeah, I think that's the best I can do with that. This is a... Because, I mean, what sort of nitrogen products? What sort of oxygen? I mean, would the oxygen be included? I mean, that's just weird. All right, nevertheless, for every 2 moles of our cytosine, we're going to produce 8 moles of carbon dioxide and 5 moles of water. Fair enough. Okay, the oxygen is going to determine how much oxygen we're going to have to use there. The nitrogen, I don't know. All right, so 0.0010 moles of our cytosine times 8 moles of CO2 for every 2 moles of cytosine means we're going to produce 0.0040 moles of CO2 and 0.0010 moles of cytosine times 5 moles of H2O for every 2 moles of cytosine is going to be 0.0025 moles H2O. All right, so where did I get those numbers? Well, even without a complete reaction, I knew that the carbon would all come from the cytosine, and the hydrogen would all come from the cytosine. So I knew we would have to double this because odd number of hydrogens wouldn't work with the even number of hydrogens here. So double that, and then 2 times 4 means 8 carbons, so we need 8 carbon dioxides. 2 times 5 is 10 hydrogens, so we need 5 times 2 is 5 waters over there. All right, so that's how I solved that particular problem. That one, a little bit iffy, just because the inclusion of nitrogens means you can't work out the exact reaction, which, I mean, you don't really need it, but maybe that's just my autism talking. I like to have the actual reaction so I can actually balance it rather than just balance a little bit of it. Makes me, yeah, I don't like it. All right, 34. Fluoxetine, marketed as an antidepressant under the name Prozac, can be represented by the following ball and stick molecular model. Write the molecular formula and calculate its molecular weight. Oof, that's a lot. That's a big one. Okay, so we have carbon, oxygen, nitrogen, fluorine, and hydrogen. So CHONF. It's a chomp. All right, so I see 3 fluorines. I only see the 1 nitrogen and the 1 oxygen. So now let's get to counting the carbon and hydrogen. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 hydrogens. So the molecular weight will be 17 times 12.011 plus 18 times 1.0079 plus 1 times 15.999, 1 times 14.007, and 3 times, we're going to need the molecular mass, oopsie. Boop, there we go. A molecular mass of, let's bring up our periodic table. Fluorine, 18.998. You'd think I'd have that one memorized by now. All right, boop. 18.998. I hear you, Sasha. What you want, little man? Just attention? You want to play with the dog? You should play with the dog. He's been getting complacent. All right, so calculator. Oops, let's move this back over here. 17 times 12.011. Whoopsie. Come on, there we go. 17 times 12.001. Oops. 11. Plus, oops. Okay. 18 times 1.0079 plus 15.99 plus 14.07 plus 3 times 18.998 gives it a molecular weight of 309.329 grams per mole. Nice to see they're keeping it fun by making the first couple of problems just counting. All right, 34. So 36. The following diagram represents the reaction of A2, red spheres, with B2, blue spheres. Write a balanced equation for the reaction and identify the limiting reactant. Okay. So, A2 plus B2 produces, A is red, so AB3. We'll need 2 of these and 3 of these. All right, so the limiting reactant was obviously B because we had red spheres left over. That is to say, we had some of the A2 left over. It can only be left over if it's not the limiting reactant. All right, how many moles of product can be made from 1 mole of A and 1 mole of B? B is going to, again, be the limiting reactant for this particular problem because you have equal quantities, but B gets used up faster. So you can produce 2/3, so it's going to be 0.67 moles. All right, so 1.0, okay. Just to reiterate, if you have 1 mole of this and 1 mole of that, this gets used up faster, therefore that 1 mole would be the limiting reactant. The only way they could be used up equally is if you had 1 to 3. So even 1 and 2, this would still be the limiting reactant. All right, so 1 mole of B2 times 2 moles AB3 for every 1 mole, or sorry, 3 moles of B2 is equal to 0.67 moles of AB3 as a product. All right, 38. Let's move this back to the Which of the following equations are balanced? The development reaction in silver halide photography. 2 silver bromide plus 2 sodium hydroxide plus C6H6O2 yields 2 silver, that's balanced, plus H2O. The hydrogen is balanced. Plus 2 sodium bromide, the sodium and the bromide are balanced, plus C6H4O2. The hydrogen is not balanced. Oh, wait. Yeah, no, the hydrogen is not balanced. We have 4 plus 2 makes 6 hydrogen on the right. We have 6 plus 2 makes 8 hydrogen on the left. So no, the hydrogen is not balanced. We lost hydrogen somewhere. The preparation of household bleach. 2 sodium hydroxide plus 1 chlorine molecule makes sodium hypochlorite plus sodium chloride plus water. Sodium and sodium makes 2. Chlorine and chlorine makes 2. Oxygen and oxygen makes 2. 2 hydrogen plus 2 hydrogen. Yes, that is balanced. Okay, so B is balanced, but A is not. All right, 640. Balance the following equations. All right, I'm pretty good at that. Magnesium plus nitric acid yields hydrogen plus magnesium nitrate. 2 of these, and we're done. That was a little too easy, because we need 2 nitrates for that, and we need 2 hydrogens for that, and that's all she wrote. Okay. Calcium carbide plus H2O. I'm not going to do the bookkeeping, because after 20 years, I don't need it. You guys should probably do the bookkeeping. Yields calcium hydroxide plus C2H2, acetylene. Interesting. I really doubt that that would work in real life, but 2 of those, 2 of those. 1 and 1, 2 and 2. I think we're going to need 2 water. 4, 2, 2. Yes. Okay, that'll do it. S plus O2 yields SO3. Yep, we're going to need 2 of these and 3 of these. Uranium 4 oxide plus hydrogen fluoride yields uranium 4 fluoride plus H2O. We're going to need 4 of these and 2 of those. Okay, 642, more balancing. Silicon tetrachloride plus H2O yields SiO2 plus HCl. 2 of those, but no, we'll need 4 of those. So we'll need 2 of those. Yep, just 2 and 4. And that balances it. Because now we have 2 oxygens, and we have 4 chlorines, and we have 4 hydrogens. Okay. Tetraphosphorus dicoxide plus H2O yields H3PO4, phosphoric acid. Oops, PO4. Okay, we'll need not 5. Oh, we're going to need 10 of these. So we'll need 4 of these. No, that's not going to cut it. Interesting, interesting, interesting. 5 of those wouldn't work. We can't get, let's say 25. Yeah, that would, no, but 25 wouldn't cut it there. Oh man, I'm actually going to, oh, I forgot, okay. So don't balance the oxygen quite yet. Well, I know I'll need an even number for that. So let's go just randomly 8 of these. 24, so I'll need 12 of those, and this would be 2 of these. So 20 plus 12 would be 32. 8 times 4 is 32. Oh, okay, so my numbers are all even, so I'll cut them in half. So 6 and 4. I should have started with the phosphorus, I guess. So 4 times 3 is 12, 6 times 2 is 12, we have even hydrogens, 4 times 1 is 4, 1 times 4 is 4, we have even phosphorus, and 16 oxygen, 6 plus 10 is 16 oxygen. Okay. CaCN2. Oh. Plus H2O. I have no idea what that guy is. Yields limestone and ammonia. So we'll need 2 of those to start with. It gives us 3 of these guys. And I think that's all she wrote. Yep. Because 2 nitrogens meets 2 nitrogens, 6 hydrogens means 3 times 2 is 6 hydrogens, 3 oxygens means 3 oxygens, and we have 1 each of calcium and carbon. Booyah. NO2 plus H2O yields HNO3 plus NO. Now we're going to need 2 of these. Oh, no, we're going to need 3 of these, because we'll need 2 of these. 2 and 2. 2 plus 1 is 3. 3 times 2 is 6, plus 1 is 7. 6 plus 1 is 7. Yep, that'll balance it. Alright, the reason I knew I needed 3 of these is because I knew I needed 2 of the nitric acids. I needed 2 of the nitric acids to balance out the hydrogen. And then 2 nitrogens plus 1 nitrogen gives us 3 nitrogens. And then everything else just sort of fell into place. All right. 44. What are the molecular weights of the following substances? Mercury 1 chloride. Calomel. Once upon a time used as a purgative. Oh, wow. I can see why they no longer used it as a purgative. A bowel purgative would be a laxative. You know, it makes you poo. So Hg2Cl2. Bring up our periodic table. Mercury is, so 200 times, 200.059. No, just 59 times 2. And mercury, chlorine, 35.453, also times 2. It's going to be 470 something. There you are. For 72.09 grams per mole. Next up, C4H8O2, butyric acid. 4, 8, and 2, 12.011, 1.0079, 15.999. Oh, you can't see my calculator. Actually, screw it. You don't need to see my calculator. 4 times 12.011 plus 8 times, dang it, 4 times 12.011 plus 8 times 1.0079 plus 2 times 15.999. 88.1 105 grams per mole. Dichloro-difluoromethane, chlorofluorocarbon. CF2Cl2. 1, 2, and 2 times 1, 2.011, 18.998, 35.453. $120.913 grams per mole. What are the molecular weights of the following? All right. C33, H35, F-N2O5. Atorvastatin. Okay, that's a blood lowering? Yeah, blood cholesterol med. It's a statin, of course, cholesterol. 33, 35, 125 times 12.011 times 1.0079 times 18.998 times 14.007 times 15.999. All right, calculator, do your work. Five, 8.646 grams per mole. Yeah, organic compounds can get really frickin' big and complicated. Carbon has the tendency to do precisely that. All right, next up. C15, H22. Oh, no. Looking at the wrong problem. C22, H27, F3O4S. Fluticasone, anti-inflammatory. That is a nasal spray. I know, because I use it. Living with a dog and a cat means I kind of get stuffy. So, 22, 27, 3, 4, 1 times 12.011 times 1.0079 times 18.998 times 15.999 times 32.066. That is sulfur, yes? Yes. $444.511 grams per mole. And finally, C16H16 ClNO2S. Which one is that? Clopidogrel inhibits blood clots. 16, 1, 1, 2, 1 times 12.011 times 1.0079 times 35.453 times 14.007 times 15.999 times 32.066. Calculator, your calculator. 16 times 12.011 plus 16 times 1.0079. 35.453. They are playing together. plus 2 times 15.999 plus 32.066. 321.826 grams per mole. All right. So, how many grams are in one mole? You're just asking for the molar mass again. Okay. So, titanium A is 47.867 grams per mole. Bromine. There are 2 atoms of that in every mole, so we're going to take the molar mass and double it. 79.904 times 2 is going to be 159.808. I mean, it's good to get practice, but come on. Mercury is 200.59, and water is 18.02. I just know those off the top of my head. I'm 650. How many moles of ions? That's good. How many moles of ions are in 27.5 grams of magnesium chloride? All right, so they're asking for ions. Well, magnesium chloride has 3 ions. Magnesium, chlorine, and chlorine. Or chloride and chloride, I should say. So, 27.5 grams times the molar mass of magnesium chloride. Magnesium, 24.305. So 92 point, divided by, 95.211 grams per mole times 3. All right, so we convert to moles by dividing by the molar mass, and then we multiply it by 3 because there are 3 ions for every unit of magnesium chloride. 27.5 divided by 95.211 times 3. 0.866, just that, moles of ions. That's a sort of distinction that can become important later on when we start talking about colligative properties and molality. We need to take into account the fact that ionic substances break up, and that changes things. All right. 52. What is the molecular weight of chloroform if 0.0275 moles weighs 3.28 grams? Neat. Okay, so you can do this with a fairly straightforward ratio. Grams per mole. 3.28 grams is related to 0.0275 moles in the same way that X grams are related to 1 mole. Okay, so 3.28 divided by 2.0275 will get us our answer. Calculator. Equals 119. Well, technically that's the limit. Okay, 27 grams per mole. All right. 52. Oh, I just did 52. So 54. Iron 2 sulfate, FeSO4, is prescribed for the treatment of anemia. Anemia means low blood iron. How many moles of iron 2 sulfate are present in a standard 300 milligram tablet? How many iron 2 ions? Okay, so iron 2 sulfate has a molar mass of 55.845, 32.066, and 4 times 15.999. 151.907 grams per mole. So how many moles and how many ions? Okay. So a 300 milligram tablet, 300 milligrams times 1 gram per 1,000 milligrams is 0. Technically, they only gave us 1 sig fig, but I'm going to pretend we have 3. Oops. Zero 0.00197 moles. All right, but they asked us not how many moles of ions, but how many ions in fact. So 0.00197 moles of FeSO4 times 1 mole of Fe2 plus for every 1 mole of FeSO4. So when this breaks up, there's 1 ion for every unit. Times 6.022 times 10 to the 23rd ions per mole. So, okay, we just times 6.022 is 1.19 times 10 to the 21st ions. So what I did was I multiplied by Avogadro's number. All right, who's next? '56. An average cup of coffee contains about 125 milligrams of caffeine. How many moles of caffeine are in a cup? How many molecules? Coffee. Do stupid things faster with more energy. Because coffee is brown, I'm going to use brown. C8H10 N42. Oops. O2. O2. 8, 10, 4, 2. 12.011, 1.0079, 14.007, 15.999. I wonder if anybody's showed up to... looks like somebody showed up for a couple of minutes. All right. $194.193 grams per mole. 125 milligrams is 0.125 grams. Oops. .44 times 10 to the negative 4th moles. And then how many molecules? Well, we're just going to multiply that by 6.022 times 10 to the 23rd. .88 times 10 to the 20th. Yes. molecules. Okay. So always double check my powers of 10, my orders of magnitude, my exponents there, because I'm kind of winging it in my head a little bit, because it's a little bit inconvenient to do those on this calculator. Okay. 58. A sample that weighs 25.12 grams contains 6.022 times 10 to the 23rd particles. If 25% are argon and 75% are another element, what is the oh, that's neat. And 75% are another element, what is the chemical identity of the other constituent? Okay, so 25.12 grams. Let's do purple. 25.12 grams. It's 1 mole of particles. So 0.7500. 75% are the other particle. Oh, wait, no. Ooh, let's see. So that's a 1/4 mole of argon. So a 1/4 mole of argon. Okay, argon is 39.948. So let's make sure I'm doing this right. 39.948 times 0.2500 see, grams per mole. Moles is equal to, oops, need my calculator. $9.987, so 25.12 minus that. So we have 15.13 grams of the other thing, but it's 0.75 moles. $20.17, so that means that we're probably looking at neon. Yep, that is neon. All right, so just to cover my thinking, what it told us was that 25.12 grams of our substance contains 6.022 times 10 to the 23rd particles. So 6.022 times 10 to the 23rd particles is 1 mole of particles. 25% of the total number of particles is argon. So that means that we had a 1/4 mole of argon. So what I said was 0.25 moles times the molar mass of argon gives us our mass of argon, 9.987 grams of argon. So our total mass was 25.12 grams. 25.12 minus the 9.987 gave us the remaining mass. And this remaining mass belonged entirely to our mystery chemical. And that mystery chemical was 0.75 moles, the other 75%. So 15.13 grams divided by 0.75 moles gives us 20.17, which is really close to the molar mass of argon, 20.180. It could also be, nope, it could not be bore or dibor. No, it's just neon. There's no other possibility there. Unless you had 3 of something. Would 3 lithium do it? Actually, Li3 might do it, but don't worry, it's neon. All right, quit having fun, John. Okay. 660. Titanium metal is obtained from the mineral rutile, TiO2, titanium 4 oxide. Oh, it could be titanium 4 oxide or titanium 2 peroxide. I don't know which. How many kilograms of rutile are needed to produce 100 kilograms of titanium? Okay, I mean, it's a mineral, so it's stable over time. It's not going to be a peroxide. How many kilograms are needed to produce 100 kilograms of titanium? Okay. So, 100.0 kilograms of titanium is 1.000 times 10 to the 5th grams of titanium. All right, and the molar mass of titanium is 47.867. So 100 kilograms of titanium is how many moles of titanium? It's going to be a lot. 2,089. Nice. 2,089 moles of titanium. Now, the thing is, when you look at the rutile, it's a 1-to-1 relationship between rutile and titanium because there's one titanium atom in every one thing of titanium oxide, titanium 4 oxide. So, just boom. Just a nice direct relationship. And then we just need the molar mass of our rutile. What was 47.867 plus 15.999 times 2. 79.865 grams per mole. Is 166.8 kilograms of TiO2. I just divided by 1,000 to get it back into kilograms. All right. 62. In the preparation of iron from hematite, Fe2O3 reacts with carbon. Balance the equation. We already did that in class. All right. 4, 3, 2, 1, down the barrel of a gun. Keep your head way down. Four, 3, 2, 1. Okay. Balanced. How many moles of carbon are needed to react with 525 grams of hematite? Hematite technically is the ore, and it's not going to be pure iron 3 oxide, but whatever. So 525 grams, 159.627, I think. Six 687. Oh, wow. I was really close. All right. .29 moles of iron times 1 mole of carbon for every 2 moles of iron 3 oxide. How many grams of carbon is that? Okay, how many grams? So we just multiply that by 12.011 grams per mole. .7 grams of carbon. Okay. Ooh, next page. Moving on to 64. Magnesium metal burns in oxygen to form magnesium oxide, MgO. Write a balanced equation for the reaction. 2 magnesium plus O2 yields 2 magnesium oxide. I'm just clever. All right, how many grams of oxygen are needed to react with 25 grams of magnesium? How many grams of magnesium oxide will result? 25.0 grams of magnesium divided by the molar mass of magnesium is 24.3. 24.305. .03 moles of magnesium, which is 1.03 moles of magnesium oxide and half that many moles of oxygen. I know it's an equal number because 2 to 2 means equal number, 2 to 1 means half as many. Which means that we're going to get how many? So 0.514 times 31.998 grams per mole is 16.4 grams of oxygen. Um, 25 plus 16.4 means 41.4 grams of magnesium oxide. But just to test that, magnesium oxide is 24.305 plus 15.999. 24.305 plus 15.999 times 1.03, 41.5. Yeah. The reason I was able to do that is because if you combine 25 grams with an equivalent, a stoichiometrically equivalent amount of oxygen, 25 plus 16.4 is 41.4. So, conservation of mass. That's what I was doing there. 66. Pure oxygen was first made by heating mercury to oxide. HgO plus, heating it up makes Hg plus O2, unbalanced. First, we balance the equation. Kind of the reverse of the magnesium equation we just did. How many grams of mercury and how many grams of oxygen are formed from 45.5 grams of mercury to oxide? It's going to be far more mercury than oxygen. Okay, molar mass is 200.59 plus 15.999. 216.59 grams per mole. .210 moles of mercury 1 oxide. That's going to make 0.210 moles of oxygen, of mercury. It's going to make half that much oxygen. Divided by 2, 0.105 moles of oxygen. .36 grams of oxygen. I'm leaving out a lot of the math just because it's boring and I want to not spend 2 hours working on this. 42.1 grams of mercury. 42.1 plus 3.36. 42 plus 3 is 45. Yeah, that'll do it. It balances out. These two numbers have to add up to this number here. Oops, I can barely read what I've written. The 42.1 and 3.36 had better add up to 45.5, and they do, barring some rounding errors. Conservation of matter. All of our mercury oxide has to turn into these two things, so these two numbers have to add up to this total mass. All right. How many grams of mercury oxide would you need to obtain 33.3 grams of oxygen? Okay. Well, oxygen, when you make it a liquid, is blue. So 33.3 grams of oxygen divided by 31.998 grams per mole times 2 HgO for every 1 mole of oxygen times, what was it, 216.59 grams per mole. .451 grams of mercury 2 oxide. All right, so that was just stoichiometry, grams to moles, moles to moles, moles to grams. All 3 steps. 68, Sonny. Silver metal reacts with chlorine to yield silver chloride. If 2 grams of silver reacts with 0.657 grams of chlorine, what is the empirical formula of silver chloride? Well, I know it's going to be AgCl, but let's go ahead. Oof. So, 2 grams of silver converts to how many moles? Nope, 107.87. It better come out 1 to 1. 0.0185 moles of silver. And then our mercury was how many grams? 0.67 something? 657. What? 0.00. Oh, wait. 926 moles of Cl2. There we go. Okay. Okay, so the reason this is kind of difficult is because we're comparing moles of one substance to moles of another. We need to break it down to atoms. So we do multiply it by 2 Cl for every 1 Cl2. So times 2. And now we get our 0.0185 moles of chlorine atoms. Okay. So that's what gets us our 1-to-1 ratio, AgCl, because, just equal numbers of moles. I was not thinking atomically. I was thinking molecularly. All right, 70. The industrial production of hydroiodic acid, HI, takes place by the treatment of iodine with hydrazine. Hydrazine is actually rocket fuel. Into H4. How many grams of I2 are needed to react with 36.7 grams of hydrazine? So because it's a rocket fuel, I'm going to do red. Because it go boom. 2I2 plus into H4 yields 4HI plus N2. How many grams of iodine are needed to completely react with 36.7 grams of hydrazine? So 36.7 grams, divide by the molar mass. What's up, puppy dog? I just took you out, didn't I? Yeah, I'm pretty sure I took you out just... Yes, I did. I took you out. Okay, well, actually, it was a while ago, because this has been taking a while. All right, but I promise, as soon as I'm done with this, we will go walkies. Hasn't been that long. You're probably okay. Okay, but anyway, times 4. 32.046 grams per mole. How many moles of hydrogen? 1.14 moles of hydrazine. Okay, so it's a 2-to-1 relationship. So 2 moles of iodine. Stop licking my leg, pup. Then we convert it back, stop it, to mass. So iodine is 126.90, so 253.80 grams per mole of iodine. .581 grams of iodine. It's only 3 sig figs. And did they ask us anything else? Yes, they do. How many grams of hydroiodic acid are produced from the reaction of 115.7 grams of hydrazine with excess iodine. So 115.7 grams of hydrazine times moles per 32.046 grams times 4 HI for every 1 into H4 times, let's see, 126.9 plus 1.079, 127.90 grams per mole of HI equals 251 grams of hydroiodic acid. That's a lot. A quarter kilo? All right. 72. Assume that you have 1.39 moles of hydrogen gas and 3.44 moles of nitrogen gas. How many grams of ammonia can you make, and how many grams of which reactant will be left over? All right. So, limiting reactant problem, pretty straightforward. All right, we are now dealing with ammonia, so I'm switching to green. 3H2 plus N2 yields 2NH3. We have 1.39 moles of hydrogen and 3.44 moles of nitrogen. Oh, no. Oh, yeah, yes. All right, so they didn't give it to us in grams, they give it to us in moles, which makes it super duper easy. It's not just that there's less hydrogen, it's that the hydrogen also gets used up a hell of a lot faster, because so that means the hydrogen will definitely run out first. This is our limiting reactant, faux show. So that will determine how many moles of ammonia and so on. So 1.39. We'll use up divide by 3, 4, 1, 3 moles of N2 used, and we'll produce twice as much of that as ammonia, so 0.826 moles of NH3 made. Okay, so we're going to use up 1/3 of this, or one third this much in terms of nitrogen. I just multiply by 1 divided by 3 to get that. Then I multiply by 2 divided by 3 to get that. So let's see, ammonia 1.0079 times 3 plus 14.07, 17.031 grams per mole means we're going to make how much ammonia? 14.068. 366. 14.1 grams of ammonia times 28.014 grams per mole. Oh wait, 3.44 minus 0.413. 3.43, no, 3.03 moles of ammonia left over. Times 28.014 grams per mole is equal to 0.840 grams of ammonia left over. All right. 74. How many grams the dry cleaning solvent 1,2-dichloroethane, also called ethylene chloride, C2H4Cl2, can be prepared by reaction of 15.4 grams of ethylene, C2H4, with 3.74 grams of chlorine? All right, for this one, I'm going to go with orange. No. Oh, for some reason, I'm feeling purple. I'm feeling purple for this chloroethane problem. So C2H4 plus Cl2 yields C2H4Cl2. Nice 1 to 1 to 1. So we have how much of what? We have 15.4 grams of this and 3.74 grams of this. Okay, I'm going to tell you straight up, this is going to be the limiting reactant. Chlorine is a much higher molar mass, so this is just a much smaller number of moles. But just to be on ye olde safe side, oopsie. Yeah. There's literally a tenth as much. There's 10% as much chlorine as there is of the ethylene. So this is our limiting reactant. Called it. So that determines how much of the ethylene chloride we can make. So that's 0.0528 moles of our C2H4Cl2. Because it's a 1-to-1 relationship. Times 1 mole of that divided by 1 mole of that. Yeah. And then we multiply it by the molar mass, because they almost certainly asked us for mass. How many grams? Yes. So 12.011 times 2, well, 28.05 plus 70.9, 98.95. That's the molar mass of this guy. Feel free to double check all my numbers. I'm not being excessively careful, as you can tell. So we can make 5.22 grams of our ethylene chloride. Now, you know what I should do? I should just have the appendix open all the time so I can double check my answers as I'm going along. That would just be the smart thing to do. All right, 76. Nickel 2 sulfate, used for nickel plating, is prepared by the treatment of nickel 2 carbonate with sulfuric acid. Nice 1 to 1 to 1 to 1 relationship there. Oh wait, is it balanced? Yes. Okay. How many grams of sulfuric acid are needed to react with 14.5 grams of nickel 2 carbonate? Where do they get the nickel 2 carbonate from, I wonder? Habertas. 14.5 grams of nickel 2 carbonate times 58.693. 58.693 plus 12.011 plus 15.999 times 3 is 118.701 grams per mole. Zero 0.122 moles of our nickel 2 carbonate, which, nice 1 to 1 relationship, is 122 moles of sulfuric acid. Somebody's calling me. Who would do such a thing? Hold on a second. I'm going to mute the microphone real quick. Sorry about that. I'm back. So nice one-to-one relationship, wasn't it? Yeah. Okay. So 122 moles of sulfuric acid. So 0.122 moles of H2SO4 times 98.078, I think it is, grams per mole. I'm going to go ahead and double check that. I am getting too familiar with these things. All right. Times 0.122, 11.96 grams H2SO4. All right. That was A. B. How many grams of nickel sulfate are obtained if the yield is 78.9%? Oh, good, a percent yield problem. All right, so it's 0.122 moles. We're doing the same deal, so it's still 1-to-1. We're going to theoretically get 0.122 moles of our nickel 2 sulfate. So the mass of that, we need the molar mass. What was the mass of nickel? Nickel is 58.693. $154.76 grams per mole. $18.9 grams of our nickel 2 sulfate. But our yield is only going to be 78.9% of that. So times 0.789. 14.9 grams. Let's see if I made any stupid mistakes in there. It's a long, tough life, full of toil and strife, we whalermen undergo. And we don't give a damn when the day is done, how hard the winds did blow. Hello, Sasha. 6 hellish months we waste away. 12 grams, yeah. And 14.9. I am on the ball. Okay. 78. Limestone, calcium carbonate, reacts with hydrochloric acid, blah, blah, blah. If 1 mole of CO2 has a volume of 22.4 liters, how many liters of gas can be formed by the reaction of 2.35 grams and 2.35 grams? Which is the limiting reactant? Okay. It's a cat. He's coming to visit. Careful, buddy. That lamp is probably super hot. Keep walking, buddy. All right, let's, yep. Over here. Okay. So, it was 2.35 grams each. That's a 1-to-2. Okay, so I'm going to have to actually put some effort into this. Not, a lot, but some. CaCO3 plus 2HCl yields CaCl2 plus H2O plus CO2. Yeah? Yes, okay. So 2.35 grams, 2.35 grams divided by, I don't know that. So 40.078. 100.086 grams per mole. 0.0235 moles divided by 35.453 plus 1.079, 36.461. That's per mole. Zero point 0.0644 moles divided by 1 divided by 2. Well, okay, I don't need to worry about that. 0.0644 divided by 2 is 0.0322, 0.023235. This is our limiting reactant. All right, so we are making carbon dioxide. So 0.0235 moles of CaCO3 times 1 to 1 means 0.0235 moles. Oh man, my handwriting's crap tonight. Of CO2. So 1 mole is 22.44 liters, so 22.44. It was 22.4 even. 0.526 liters. Yes. Okay, so that was 0.526 with the calcium carbonate as the limiting reactant. My handwriting notwithstanding, my chemistry still is excellent. That's right. Keep panting heavily on my leg, Papa Dog. All right. 80. Acetic acid reacts with isopentyl alcohol to yield isopentyl acetate, a fragrant substance with the odor of bananas. If the yield from the reaction of acetic acid with isopentyl alcohol is 45%, how many grams of isopentyl acetate are formed from blah 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 and blah blah blah? Okay. So let's power through. Power through, pup. Let's power through. HC2H3O2 plus C5H12OH yields C7H14O2 plus H2O. Okay, we have how many grams of each? 3.58 and 4.75. Molar mass of acetic acid. And the molar mass of our isopentyl alcohol. Wow, really close. All right, but nevertheless, one-to-one relationship. The alcohol is our limiting reactant. So they asked how many grams we can make of our product. 45% yield. Okay. So we're going to make 0.0533 moles of our product times 0.45. 0.0240 moles of our product. And the molar mass of our product is, let's go ahead and just use parentheses. Times 7, 14 times 1.079, 15.999 times 2. Close parentheses. Bam. That was times 130-ish. Means we made 3.12 grams of our product. And according to the book, I was close enough. I don't know. It's probably just rounding errors. Or I could have slipped a digit somewhere. Don't you on my desk? What's wrong with you, pup? All right, so that took me up to 680, and now I believe we can finally stop just counting correctly. Oh, 84, 86, 88, 90, 90. Okay, you know what? I'm getting tired, and I've been doing this for more than an hour, so I'm just going to stop for the night. I will pick this up tomorrow with the rest of the problems from the end of Chapter 6. Thank you for watching. I love you all very much. Go to bed.